Helen Sawyer Hogg, the typical RAS greeting. Say your name, where you're coming in from, how's your sky? I was just telling Robin, I went outside for 5 minutes, but I had to come back in. I feel like I'm having heat stroke already. But and we are live on YouTube, so hello, YouTube friends as well. We'll be monitoring both chats. I'll be monitoring both chats, and I will be sending any questions from the YouTube chat over to the Zoom chat. So don't feel left out over there on YouTube. And we'll give probably a minute, let people file in, make sure they have all the right links, and then we'll get started.
Judging from our early adopters in the chat, everyone's already an old pro at this, but just a reminder to switch the little blue tab there to everyone and not just to say host and panelists if you want to say hello to everyone. So just change that little blue drop-down menu.
And for those of you who
Lawrence, Kansas. Okay, there's someone.
Hi, Jenna. For those of you who probably have already guessed, my name is not the Royal Astronomical Society of Canada. I just forget to change it.
Ottawa, Victoria, all sorts of people. Southeast Alberta. Keeping it mysterious. That's good.
Okay, I'm just going to say hello to our YouTube. Say hi. And hello, RAS Montreal in the YouTube. And I think people are slowing down. 30 more seconds, then we'll pass it.
Yeah, if you could give a few more seconds, it's still climbing.
Yeah, I said a couple more seconds.
Yeah, we're going to break 100 in a moment.
We broke 100. That's good.
Oh, there we go. Yes.
Yeah.
We're almost as popular as Insider's Guide. Portugal Cove.
Yes, that's Newfoundland, right?
And so we've had some questions a couple times about our recorded sessions. We don't have any plans right now. They're going to be up either Tuesday or Wednesday. As I said, I have to edit these cloud recordings down into their individual sections, and it will depend how long that takes me. And then we don't have any plans to knock it off anytime soon. Our website is not going down. We have a year subscription minimum for that. So don't worry, you don't have to watch it all in a week.
Lots of time to catch up.
Maybe Christmas we'll decide. Okay, I think we've set it out here. So I am going to hide away, and I will pass it off to our president, Robin, and the executive director, Phil Groff, and they will introduce our keynote speaker.
Thank you, Samantha.
Thank you, Samantha.
Well, good evening, everyone. My name is Robin Ford of the Calgary Centre, and I'm the president of the Royal Astronomical Society of Canada. Before we move on to the evening programming, I want to take this opportunity to thank all of today's presenters and our organizers. It's been an amazing day. And with 3 distinct tracks, it was impossible to see everything. And as Samantha just mentioned, hopefully you enjoyed the sessions you participated in, and know that the sessions that you may not have seen that you want to will be available as a recorded session. Also, since we likely have participants this evening that weren't part of our opening this morning, and in the spirit of truth and reconciliation, I would like to acknowledge that we live, work, and play on the traditional territories of the people of the Treaty 7 region in southern Alberta, which includes the Blackfoot Confederacy, comprising the Siksika, Piikani, and Kainai First Nations, as well as the Tsuut'ina First Nation and the Stoney Nakoda, which includes the Chiniki, Bearspaw, and Wesley First Nations. The city of Calgary is also home to Métis Nation of Alberta Region 3. This evening, it is my honor and pleasure to welcome you to the 2022 RESC General Assembly's Helen Sawyer Hogg Memorial Lecture. Helen Sawyer Hogg was a notable woman of science in an era where many universities would not award scientific degrees to women. Considered to be a great scientist and a gracious person over a career of 60 years, Helen Sawyer Hogg is an important and well-recognized figure in the RASC's history, and her phrase, "the stars belong to everyone," is echoed in and inspires much of what we do. And our guest speaker this evening offers a great representation of Helen Sawyer Hogg's message that the stars belong to everyone. I'm honored to introduce Dr. Ouellette, and as a father of 3 daughters in STEM, I'm sensitive to the challenges that women still face in STEM. And I really hope that the participating young women in the audience tonight and their parents and their grandparents are inspired by Dr. Ouellette and her work. So a little bit about our presenter tonight. Dr. Nathalie Ouellette is an astrophysicist, science communicator, and lifetime lover of all things space. She obtained her PhD in physics and astronomy at Queen's University in Kingston, Ontario in 2016. Her research focuses on galaxy formation and evolution, particularly those found in clusters. Nathalie is currently the coordinator of the Institute for Research on Exoplanets, many of you know that as IREX, at the University of Montreal, and is also the outreach scientist for the James Webb Space Telescope in Canada, collaborating with the Canadian Space Agency. Very, very, very topical and exciting. Where was I? She's a frequent contributor and analyst in Canadian media on everything related to space. She also organizes and participates in science outreach events from local to international scales to encourage the interest and participation of youth and the general public in space science, and to increase scientific literacy in Canada. So please join me in welcoming Dr. Nathalie Ouellette, our Helen Sawyer Hogg Lecturer for 2022. Nathalie.
Well, thank you so much, Robin. And thank you for the invitation, for selecting me. I've never had the chance to meet Helen Sawyer Hogg, but I've heard so many fantastic things about how she was gracious, generous with her time, a lover of science, but also seeing the importance of sharing science with the greater public, but also feisty when she needed to be. And that is the person that I hope to be remembered as well. And I know I'm still relatively early in my career. I've still got lots and lots of stuff to do, but I feel extremely fortunate to have been given all the chances that I have up until now. So thank you again for this great invitation. So I'll go ahead and share my screen now. And can you confirm that you see that? Perfect. All right. So it was a really hard thing for me to try to figure out exactly what I was going to talk about today. Obviously, James Webb was going to be a big focus, but there's just so many exciting things for me to talk about right now. So I wanted to give a little bit of an overview of why I think this is a golden age for space astronomy and how we are at the dawn of a cosmic revolution. So I'll be talking about several different projects that Canada is involved in, some that I am involved in as well, and how we are really close to answering some really, really important existential questions almost about our place in the universe. But before going into that, I just wanted to take a few moments to mention some of the really great connections that I have with RASC, the Royal Astronomical Society of Canada. So some of you might know me from way back when, over 10 years ago now, which is a significant portion of my career. So as was mentioned, I did my graduate studies in Kingston at Queen's University. And instead of being a teacher's assistant, I had the great chance of being the observatory coordinator on campus. So I was handling all of the open houses, but I wasn't doing that alone. I was so well supported by the Kingston Center of RASC. It was really fantastic to collaborate with them with the open houses. And we often joke in professional astronomy how professional astronomers can point out the full moon in the sky, and that's about it. So I had really fantastic support from people that were real experts about the visual night sky that you could see at night and the use of telescopes as well. So I'm so grateful for all the guidance they gave me. And they played a non-trivial part in making me choose science communication as a career instead of pursuing purely research afterwards. And of course, I've had connections with so many different RASC centers since leaving Kingston, Ottawa, Okanagan, all over the country. But I have to say a special mention to the great people at the Montreal Center who have been so welcoming since I've come back to Montreal in 2018. They've given me such a good place to be able to talk to their membership, talk to the general public, give me great great platforms. And I've really appreciated all your friendship and all your guidance and support throughout my career. And I look forward to continuing all these collaborations. So I always like to mention how astronomy is probably the oldest science in humanity because it's so simple to do. You don't even need an instrument really to appreciate the night sky. Obviously, you don't get this beautiful night sky in a place like where I was born and raised, Montreal, but you can still observe some really fantastic things, even in certain light polluted areas. So we've been able to do astronomy for millennia, just with our naked eye, just looking at the stars and the planets, seeing how they change over time. But we are, I think, at the dawn of a cosmic revolution, because we have so many fantastic tools now to do astronomy in lots of different ways. And one of the things that I'm really excited about is the fact that we can now look and listen at the universe in all kinds of different lights, different signals. So this is looking at the universe through the entire electromagnetic spectrum. So obviously, we've been doing visible or optical astronomy for a very, very long time, just because that is the same kind of light that we can see. So the instruments we need to build are quite a bit more simple, just using lenses and mirrors. But the universe is very chatty in lots of different kinds of light. So going all the way from gamma rays and X-rays, very, very energetic light, to long wavelengths like radio waves. But the issue is that we live on planet Earth that has an atmosphere. It's a good thing that it has an atmosphere because that keeps us alive. We need it to breathe. We also need it to protect us from very dangerous cosmic radiation. So you can see here that our atmosphere is transparent to only certain types of light. So visible light, which is very handy for us because we use that to get around. Radio waves are also very easily transported through the atmosphere. So we've depended on radio waves to do telecommunications. But very energetic gamma rays, X-rays, ultraviolets, those are blocked out, again, thankfully, because those are very dangerous for us. A lot of infrared light as well are blocked out by the protective atmosphere. But we've developed lots of different tools and we've been able to place them at different places to look at these different types of light. So we have space telescopes up in the sky that can look at X-rays, look at ultraviolets, look at infrared. We've also utilized ground-based astronomy to look at the kind of light that can pass through the atmosphere. And we've been able to build very, very large telescopes and, for example, radio dishes to really maximize our collecting power for those types of light. But on top of that, with multi-messenger astronomy, we can now look even beyond light at gravitational waves, looking at gravitational waves caused by the collision of very, very dense objects, or even astroparticles, trying to figure out what the deal is with neutrinos or what the true nature is of dark matter. So we are now able to do all of this. And some of this is quite recent. Astroparticles, it's only been a few decades. Gravitational waves, it's only really been a few years that we've been able to detect them. So we've never been so capable to study the universe, looking at all these different things. And it's important to look at all these different types of lights and signals because different things in the universe shine in different kinds of light. You can even take something relatively simple like a galaxy, and depending on the type of light that you look at, you're seeing different parts of that galaxy, different phenomena going on in that galaxy. So here you have the Whirlpool Galaxy, a great favorite of mine, and you can see it from radio waves all the way to X-rays. So depending on what kind of light you're looking at, you're either looking at the core, or you're looking at the gas throughout, or you're looking at different populations of stars. So we really need to be able to look at all these different types of light in order to do astronomy properly. And obviously, putting things in space is a key feature of that, just because we can get above the atmosphere of the Earth. So when you talk about space astronomy, you can't not talk about the Hubble Space Telescope. It's not the only space telescope, of course, but it is probably the most well-known of NASA's great space observatories. It has had a lasting legacy in science, but also in the public understanding of astronomy. And it's still going strong, although it is getting quite old. But it's done really fantastic science, fantastic outreach since it was launched in 1990, especially since it was fixed in 1993 using the Canadarm with a little rescue mission with some astronauts. But it's been going for over 30 years now. And so the instrumentation, the tools on it are starting to get old. But it has already done great work and has built a legacy for different kinds of science. Being someone who studies galaxy formation myself, I am partial to the Hubble Ultra Deep Field. So this was something that was really fantastic, where we've been able to look at how many galaxies are truly in the observable universe. And we're talking upwards of 1 trillion galaxies here. And we've been able to map them in a 3D space. So many of these galaxies were totally invisible to us before we were able to look at them using the Hubble Space Telescope. And we were able then to really place them in the entire universe and see how rich the universe actually is. And this is one of the reasons why we decided to build telescopes in the future who could look even farther back, because these are not the first galaxies ever created in our universe, but this piqued our curiosity and we wanted to go even deeper. Although I love galaxies, there are other really important fields that Hubble contributed to, and one that we can't not mention are exoplanets. And this is particularly interesting because when Hubble was first conceived and even launched into space, the first exoplanets hadn't really been detected. There were a few murmurs in the late 80s, early 90s, but nothing totally confirmed. But this concept of other worlds and exoplanets has existed for a long time, hundreds of years. We know that we live in a solar system that has a star at the center and has planets orbiting that star. So for a long time, scientists and philosophers have theorized that other stars in our sky could also have planetary systems as well. So this concept of an exoplanet dates back from very, very long. But as I was saying, we are truly in a special time right now in humanity, because we only now have tools that are sensitive enough to detect these exoplanets directly or indirectly. So the first ever exoplanet ever detected, and there's a little asterisk there because depending on who you ask, this might not be the first because we had detected some around pulsars before then. This is certainly the first exoplanet ever confirmed with confidence around a sun-like star, and this was in 1995 in a system called 51 Pegasi. That was the star. So this was the first exoplanet ever discovered, and it was a great revolution. It was the first one that we confirmed, but not only because it was the first one, but also because of the type of exoplanet it is. So this is a planet about half the mass of Jupiter, slightly larger than Jupiter, so less dense, quite puffy, with an extremely close-in orbit. So if you take this orbit of 51 Pegasi b, you can actually plot it compared to the orbits of the terrestrial planets in the solar system, and you can see it is considerably closer than Mercury even. So we have this large Jupiter-like planet, very, very close into its star. It takes only 4 days for it to go around its star. So we named this kind of planet a hot Jupiter. But we didn't think this kind of planet could even exist because the heat and the radiation from the central star, we thought, should blow off the atmosphere of such a gas giant. So this completely changed our idea of what kind of planet can form, because we had no example of this before. And since we've been able to detect a large variety of different kinds of planets. So this explosion in the domain of exoplanets has birthed many different institutes all over the world. And so if you're not familiar, I work at one of these institutes in Montreal, and we have members across 5 now actually institutions in Quebec. So we're over 60 permanent researchers, graduate students, and in the summer we even go up to about 80 with summer students. And we're all looking for these exoplanets, these new worlds, and searching for alien life. So we are the largest exoplanet research institute in Canada, one of the most competitive internationally, and many people don't even know that we exist in Canada. So one of my jobs is to try to get people excited about exoplanets and make them realize that in Canada, we have a real expertise in this field. But why search for exoplanets? What answers are we trying to seek in searching for these exoplanets? So we're trying to answer several questions here. Obviously, I'm preaching to the choir in a certain sense here because you all love space. That's why you're here. But sometimes the public wonders why we're interested in putting money and resources in looking for other worlds when we have a lot of issues on our own planet. And that is a totally fair comment and question to have. But searching for exoplanets actually gives us a lot of context about our own world. So one of the questions we're trying to answer is how our solar systems formed. So we still have a lot of questions related to how our own solar system was formed because we live on the Earth, which has a climate, water, and atmosphere, erosion, plate tectonics, which has erased a lot of the evidence of what was going on in the very early solar system. We have asteroids and comets that can serve as sort of fossils or time capsules of what was going on then. But we can also look at other solar systems being formed and try to take clues from that and figure out what was going on in our own early solar system. We also want to know if Earth is special. And if we can convince people that Earth is quite special and unique, hopefully that convinces people to take better care of this own Earth. But we are looking for Earth 2.0s or Earth analogs, not in the interest of moving there, but just to see how prevalent those conditions are, because we also want to know, are we alone in the universe? Again, we have a lot of questions about how life was started on our own planet. So if we can find in what kind of conditions on other planets life can form, we might be able to answer how rare the type of life we see on Earth is as well, and how that life came to be. So even though we're looking outwards, searching and looking at exoplanets is actually a quite introspective science, because we're really trying to understand a lot of ourselves as well in doing so. So how to search for exoplanets. So just a few little pointers here. A lot of this will be a refresher for many of you. So the easiest way to do this is using what we call the transit method. So quite similar to an eclipse, but with a planet instead of a moon, you can sometimes see a planet passing over the disk of a star by seeing the light of that star periodically dim. So we can't actually see this visually, but if we're looking at the brightness of the star, we will see the brightness go down. And depending on the depth, how much of the dimming happens, we can actually tell a lot about the size of that exoplanet, its period as well, how far it is from its star. We can actually get a lot of information. Even though this is probably the easiest way to detect an exoplanet, the first exoplanet ever detected was not done using that method. It was actually done using the radial velocity method. So what happens here is we are looking at the star that may have an exoplanet orbiting around it. And because the planet has some gravity to it and some mass, it might be tugging through gravity on that star. So we see a little wobble in the star, the central star, and we can see that movement, that dancing or that wobble in the way that absorption lines in the spectrum of that star is shifting. So the bigger the planet, the closer into the star, the more these absorption lines will be visibly wobbling. But we're getting to the point now where we can see very, very small wobbles that are equivalent to an Earth-sized planet that is pulling on small stars. So this is really a fantastic way to get supplemental or complementary information like mass, which you cannot get using the transit method. That is a little bit unsatisfying because those are indirect methods of finding exoplanets. There is one way that you can do it directly. It's called direct imaging, but it is very difficult. So we don't have that many exoplanets that have direct images of them. Because typically a star at the center of a system is much, much brighter than the exoplanet going around it. It's sort of the equivalent of trying to see a small light bug going around a big lighthouse that's shining out into the horizon. Typically, we're talking about a star that's about 1 billion times brighter than its exoplanet. So there's only very few conditions where we can actually take a real picture of an exoplanet going around its star. But this is actually a Canadian specialty because the first time this was ever done for a planetary system with multiple exoplanets was by Canadians in Canada using a Canadian instrument. So this is HR 8799, and you can actually see 4 exoplanets here. And we were able to observe this system for several years and see these planets orbiting around the star. But one of the reasons why we could actually take this picture, it was a long, arduous road, and I worked with a lot of the people who actually accomplished this fantastic discovery. A lot of it was related to data processing, cleaning up the image, but the system itself was such that it made it easier or possible for us to take this picture. So typically what you have to do when taking such a direct image is block out the central star with a mask, because otherwise that glare is drowning out everything. But that means that the planets themselves have to be relatively far from the central star for you to be able to see them. And the planets themselves also have to be quite large for them to be large and bright enough for us to actually see them in a direct image. So this first direct image of an exoplanetary system was taken in 2008 using an instrument at Gemini North, which is partially owned by Canada. So you see 4 exoplanets, and they are all 7 to 10 times the mass of Jupiter. So very, very large. And they're very far from their star, like I mentioned. So the orbital periods are between 45 years for the one that's closest in and 460 years for the farthest one out. So to give you some insight on how far that is, Pluto, of a very distant dwarf planet from our sun, takes 270 years. So this really distant one is nearly twice as far from its star as Pluto is from our sun. So this discovery was made by Christian Marois, who works at NRC in Victoria, René Doyon and David Lafrenière, who are both my colleagues at the University of Montreal. So this really caused an explosion of interest in exoplanets in Canada and in Quebec especially, which is why we are so active in this field in Canada now. So since these few initial discoveries, we have detected a plethora of more exoplanets, over 5,000 now. So these are all artistic representations, obviously, but we can still find a lot of information using direct imaging or the indirect methods that I mentioned, including the size of these planets, whether they have rings or even big systems of debris and rocks and asteroids. And we're even getting to the point where we might be able to detect exomoons or moons that are orbiting around these different worlds. So this is what I like to call the exoplanet zoo. So we have big gas giant type exoplanets, small rocky ones that are closer to the Earth. Some of them are very close into their star. Some of them are very far away. And we are detecting lots of different types of planets that are very different from what we have in our own solar system. Lava worlds are very rocky planets that are very close into their star, so much so that they have oceans of magma covering their surface. Ocean worlds that might be totally covered by water, all different kinds of planets. So we recently crossed the threshold of 5,000 confirmed exoplanets. And with so many surveys ongoing for exoplanets, we're continuing to increase that number every single day. And every day we get a little bit closer to maybe finding an Earth 2.0. And in doing so, we're particularly interested in searching for planets that are in what we call the habitable zone. So the habitable zone being the distance from a certain star that is at the right distance for that if there was water on that world, it would be in liquid form. So it's not a guarantee that it's habitable. It's not even a guarantee that there's water there. It just really means that the solar irradiation in that section of the planetary system is right between 0 and 100 degrees Celsius, roughly. So we are smack dab in the habitable zone of the solar system, but Venus is sort of on the edge of the habitable zone as well. And we know, and for the most part, Venus is not a very habitable world. Sarah Seeger will tell you about some of the places on Venus where we might be able to find life. So you'll be able to find out about that tomorrow. But for the most part, Venus certainly doesn't look like the Earth. So just because something is in the habitable zone doesn't mean that it has a lush countryside and beautiful oceans where life can come to be. But it's a good starting point to try to find these Earth-like planets. So we found about a dozen of them at this point, what we call potentially habitable worlds that happen to be in this habitable zone and that are also rocky. So we're technically looking for things that look a lot like the Earth, a mass similar to the Earth, a size similar to the Earth, and in the habitable zone. And we are developing tools to look for more and more of these worlds. And we have a lot of really encouraging recent discoveries. One that I can share that was from 2019 was the first time we detected water vapor and clouds on an exoplanet in the habitable zone. So the name of this exoplanet is K2-18b. So it's a world that's a little bit bigger than the Earth. So we don't necessarily think that it is a rocky planet, but it certainly seems to have an atmosphere with water vapor inside the atmosphere. And there's also a good chance that there might be precipitations of liquid water in this world. So this discovery was made by my colleague, Björn Benneke, and his team at the University of Montreal, again showing that we are very competitive here in Canada and at the University of Montreal in all of these different studies of exoplanets. So how exactly are we trying to sort of streamline this great search for trying to find alien life in exoplanets? So there are certain types of telescopes like Kepler, which is now retired, and its replacement, TESS, that are really, they've been made to essentially find as many exoplanets as possible. There's also some of them that are on the Earth, like this TRAPPIST observatory, and you don't even need a very large telescope to do this. So these are telescopes that are trying to find exoplanets using the transit method, sort of the easiest way to find exoplanets. So they're staring at thousands or even hundreds of thousands of stars simultaneously and measuring dips in the light of these different stars. So with these telescopes, we were able to find thousands and thousands of exoplanet candidates, but that's not sufficient. We need more information about these exoplanet candidates in order to move forward and maybe find out if they harbor alien life. So the next step after this is often picking out the most promising candidates from these big, huge catalogs of thousands of exoplanets and finding ones that we want to do further studies using the radial velocity method. Because as I mentioned, that allows you to determine the mass of these exoplanets. And if you have the size of the exoplanet from the transit method and the mass of the exoplanet from the radial velocity method, you can then find the density, which tells you about the composition of these worlds. That starts telling you if it's a rocky planet or a gas giant planet. So we have two instruments that were very recently built and actually commissioned. So Spirou is a spectropolarimeter. So it looks at that wobble of the star that I mentioned, and it began its operations in 2018 at the Canada-France-Hawaii telescope on Mauna Kea. But that looks at the northern hemisphere. So we wanted to have a twin of it looking at the southern hemisphere. So we created NIRPS, the Near Infrared Planet Searcher. And we actually just finished the first flight of this instrument. So it's going to begin its scientific operations very, very shortly. And they are able to find Earth-sized planets around cool red dwarf type stars, which are the most prevalent type of star. So this sort of like narrows the kind of planets you want to look at, because then it tells you, okay, this is an Earth-like planet. It is a rocky planet. So our big catalog from the transit method is sort of narrowed down to something smaller using radial velocity instruments. And after that, we can really do detailed studies of these different worlds using something like the James Webb Space Telescope, which is really going to be looking at the atmospheric composition of these different exoplanets. So this leads me to my favorite mission that we are currently a part of, and my favorite mission as a whole, the James Webb Space Telescope. It's an international collaboration that's led by NASA, but as many of you know, has a very important contribution from the European Space Agency, who is also a partner in Hubble, and the Canadian Space Agency, which is, of course, for us, particularly exciting as Canadians. And Canada, although slightly involved in Hubble because we had Canadian astronomers use it, and we harbored a lot of the data from Hubble, and the Canadarm sort of saved Hubble and its sort of wonky optics. We weren't formally part of that collaboration, but we are now formally part of Webb. So I truly hope that this is just a blueprint of the future of space astronomy in Canada, being involved in these flagship missions that are basically the largest space astronomy missions in a generation that we have. So my role for this mission is the outreach scientist for Canada. I'm part of the scientific team, but I act sort of as a bridge between the science team and the general public. So it's my job to make sure that everyone in Canada knows what their hard-earned taxpayer money has gone to, and all the amazing science that we're able to do with Webb. And not only the amazing science, but the really fantastic spin-off technology that we've been able to create because of the technology that was developed for Webb as well. So this is a nice picture just before the pandemic where I got to visit the telescope. But if you truly want to see my dedication to this telescope, I prefer showing this image from last Halloween. Clearly, I have too much time on my hands during the pandemic, but this is a picture of my Halloween costume. And I didn't go trick-or-treating, but I gave out candy dressed up as the Webb telescope, and many people recognized what I was. So I really enjoy having the chance to do outreach in unusual ways, ways that are a little bit different, in the hopes of connecting with people sort of differently. So I really enjoyed making this, and I'm planning on rigging it up so that it can hang in my office somewhere. So the Webb telescope is something that's been going on for many decades now. It started being conceived of as a project when Hubble was just at the start of its operations in the 90s, because we know that these things are built over many, many decades. So for the last several decades, we've been concentrating on building the instruments and doing very important tests on the telescope, the instruments, the whole observatory itself, because we knew that we couldn't have the same thing happen to this telescope as happened with Hubble, because we were sending this telescope out in a part of the solar system where we didn't have access to it. So for a very long time, we were doing very important tests to try to simulate the environment of space on the telescope to make sure that everything was going to go well. It was going to be able to deploy and function properly in the harsh environment of space and survive the very violent environment of launch as well. So all of those tests were completed last summer, and it was then packed up and shipped out to Kourou, where it was launched from. So this was one of the contributions of the European Space Agency. So we were able to launch it from the Guyana Space Center in Kourou. So this was a long journey of about 2 weeks, where it was on a super secret boat. Very few people knew which boat it was on, because we were actually concerned that it was going to be stolen or kidnapped by pirates and taken for ransom. This was a real concern. So there were a bunch of decoy boats that were sent out. Very few people knew which boat actually had the telescope, but luckily, after 2 weeks, it passed through the Panama Canal and arrived safe and sound in Kourou at the beginning of October of last year, where it was then prepped for launch. And one of the ways that it needed to be prepped is before it was shipped, it needed to be folded up into its stowed configuration, because this telescope is so huge that we don't actually have a rocket large enough to accommodate it unless we fold it on itself. So you can see here a diagram of the Ariane 5 rocket, the European Space Agency contribution to send it up into space, a very reliable rocket, one of the largest ones that we have as well. And the telescope is all folded up on itself like a piece of origami and perched at the very top of this rocket here. So this is the first time we've ever had to conceive of a telescope that can do this. So that was quite nerve-wracking. And the launch was scheduled in December, and because of a few delays, technical delays and weather delays, it happened on Christmas morning. This was not planned. We didn't particularly want it to be Christmas Day, but it was a really fantastic Christmas present for all the astronomers in the world. But you might also remember that in December, we were sort of in the peak of the Omicron wave of COVID. So many of us had plans to go all over the world. I was supposed to go to Baltimore, where the Telescope Operations Center was. Lots of people were supposed to go to Kourou to see it launch. And many of us had to cancel our trip, unfortunately. But we got to watch it with our families or with our colleagues from home. And I still got to tune in, make sure everything was okay. But we still had some Canadian representation in Kourou. Don't worry. So these are the 3 Canadians that were there. Here you have René Doyon, who's the principal investigator of the Canadian contribution. And he's been working on this for over 20 years. So we were very, very happy that he got to see his telescope launch into space. This is Begonia Villa, who used to work with Honeywell Canada, the main industrial partner in Canada. And when her contribution with Honeywell was over, she was then picked up by NASA because she did such a great job. So an astrophysicist by training who turned into an engineer. And this is Dave Aldridge, who still works with Honeywell Canada. He's one of the lead engineers who helped with the Canadian contribution to Webb. So we still had Canadians there who got to look at our little baby be shot up on a rocket ship into space. So I'm sure many of you got to watch the liftoff, watch the launch not in person, but live that day. But I still decided to show a little bit of the launch video, just because it's still an incredible moment that gives me goosebumps.
à tous de donner attention pour les décomptes finales. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And liftoff.
Allumage EAP, décollage.
Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds, 20 seconds into the flight, good pitch program reported.
Trajectoire est nominale.
So one thing that you might have heard at the very end there is trajectoire et nominale, and nominal, which is a French word for basically like perfect, nominal, it started trending essentially on Twitter and everything, just because we were so pleased at how well the launch went. Some of you might know that it went so well that we didn't need to correct the course of the telescope that much afterwards. We saved a lot of fuel, which ended up prolonging the estimated lifetime of the mission. So a really fantastic launch. I think all the bad luck for the telescope happened before launch, and it's been going really fantastic ever since. So as I mentioned, I was supposed to be with my colleagues in Baltimore at the Space Telescope Science Institute during this moment, but I couldn't be there. And so instead I watched this live with my family at home, and my partner thought it was a good idea to commemorate this event, this moment, by filming me while this was happening. So I won't show you the video, but I'll show you how seriously we take our projects as astronomers. This is what I looked like during the launch. I was extremely emotional. I had my Kleenex box with me. This particular moment is when the outside shell of the rocket peeled away from the telescope, and the telescope was completely exposed. It just seemed like so vulnerable in that moment. I was like so anxious and worried, but obviously it all went perfectly well. But we take our space telescope launches very, very seriously, clearly. And another really fantastic moment that we had a camera that was installed on the upper stage of the rockets, so we could see the final detachment of the space telescope from the rocket boosters. So you can see right below the telescope here. And we also got to see the solar panel come out right on time, 30 minutes after launch here. So I want to show the video, but if you're interested, I really do suggest that you watch it. It's a beautiful video. You can see the Earth in the background. Obviously, the launch is just the start of this whole adventure. Because this telescope was folded up on itself, we needed to then unfold it or deploy it in order for it to start functioning. So this didn't happen while the telescope was parked next to the Earth, because we needed to keep that rocket momentum going in order for it to reach its final destination, 1.5 million kilometers from Earth. So this was happening while it was moving. The deployment happened over the course of 14 days. We initially called it the 14 days of terror because there were over 300 single point failures for all the mechanisms that could go wrong and basically sink the mission before we could even get it started. But luckily, again, everything went to plan. One of the things that we were particularly worried about was the deployment of the solar shield on the telescope. Because of the type of telescope that this is, the telescope needed to be kept at very, very cold temperatures. So this sun shield, which was 5 layers of a very reflective material called Kapton, which had the equivalent blocking power of an SPF of 1 million for sunscreen. It had about 132 little springs and knobs and all kinds of things that needed to deploy properly for that sun shield to deploy. So again, very nerve-wracking. We actually had some issues with the sun shield when we were doing tests during those first initial years, but everything went really well. And another important feature of this telescope, because the mirror is so large, 6.5 meters wide, it's a segmented mirror, it couldn't be one giant piece. So it's 18 little segments, all hexagon shapes. And the mirror, the primary mirror itself, was folded with little wings on the side. So the secondary mirror needed to emerge out, the secondary mirror quite large also. And then the wings needed to be folded out as well. So a very large telescope. So deployment again, 14 days, and it took about 30 days total for the telescope to reach its final destination, which is a point called Lagrange 2 or L2. So Webb is on an orbit around this point, L2, and it's actually orbiting it. It's not exactly at the middle of this Lagrange point, but this Lagrange point is always directly behind the Earth. So lots of advantages of staying there. You can stay around L2 with very minimal fuel, so you can make the mission last longer, but you don't want to be exactly at L2 because then you are always in the shadow of the Earth. And because it has solar panels, it needs solar energy to function. So you actually want it to be around. So this is not the first time we've launched a telescope at L2, but certainly the most complex mission we've ever launched there. So again, this is not accessible to humans. So we wanted to make sure everything would work out the first time. And it has up until now, very, very good. So this is an infrared telescope. That means that if the telescope itself gets warm, it will start radiating and causing its own light pollution, which is why we needed that very important sun shield, like I mentioned. So there is a hot side and a cold side to this telescope. The cold side having the mirror and the instruments, the hot side having the solar panel and the communications array. So there's a big temperature difference between these two different sides. On the cold side, you're at minus 233 degrees Celsius, or just 40 degrees above absolute zero. So very, very cold. And there's even one instrument called MIRI that needs to be colder than that, about 7 degrees above absolute zero. Whereas on the hot side, you're at 85 degrees Celsius. But for the most part, except for MIRI, all of this is what we call passive cooling. So there's no refrigerant, no cooling system. It's only the sunlight being blocked out by the sun shield. So again, emphasizing how important that sun shield was. So we can compare the two telescopes here. We often call Webb the successor of Hubble, not the replacement, because they're very complementary. And we're hoping that Hubble will continue to function for many years and help Webb do its science as well. Hubble has a mirror that's 2.5 meters wide and looks mostly in the visible light, and the whole observatory is about the size of a school bus. So still quite large, but Webb is closer to the size of a small house. So the sun shield is about the size of a tennis court. The whole thing is 2 stories high. The mirror, again, 6.5 meters wide. And it's looking mostly at near and mid infrared. So not visible light, not light that is visible to the human eye. So why are we looking at infrared light here? So as I hope I've convinced you with my first few slides in this presentation, the universe is very, very interesting at all different types of light, not only in the visible light. So there's certain objects that shine particularly brightly in infrared light, even though we can't see it. So planets in our solar system, like this little image of Jupiter taken by the Juno probe, faraway solar systems that are being born. So they're protoplanetary disks, all that sort of gas and dust that's coalescing to turn into the central star and the planets. Exoplanets, brown dwarfs are also very bright in the infrared. And we've had infrared missions before, such as the Spitzer Space Telescope, but Hubble is looking at visible, but Webb has a mirror that's about 100 times larger than Spitzer. So we're really breaking ground in terms of the resolution and the power with which we're looking at infrared objects in the universe. Another reason why we're interested in infrared light is because we wanted to look at those very first galaxies that I mentioned that are born just after the Big Bang. So because of a phenomenon called redshift, which is caused by the expansion of the universe, those very, very first galaxies, which were actually quite blue or very bright in the ultraviolet light, their light is actually being stretched out into red and infrared colors because of that expansion of the universe. So Hubble actually couldn't see these very first galaxies. These galaxies are invisible in the visible light. Ironically enough, you need an infrared telescope or an infrared instrument to see those very early galaxies. And that was one of the first drivers of making Webb an infrared telescope. Finally, we can see lots of things in the infrared that are invisible essentially to us when we're looking at visible light. So this is a very iconic image taken by Hubble of the pillars of creation in the Eagle Nebula. But if we look at exactly the same spot in the sky in infrared light this time, we can actually see through the cosmic dust in that nebula, because cosmic dust blocks out visible light, but it's transparent. to infrared light. So you're opening up a whole new window when you're looking at infrared light, not only to look at certain objects in the infrared light, but looking through other components like the cosmic dust inside of nebula. So we've been doing really well, doing what we call commissioning. It's sort of like getting the telescope ready for scientific operations. And one of the first things we needed to do was align the telescope's different mirror segments. So initially, all those 18 little segments were sort of doing their own thing. And we don't want that. We want them to act all as one single unit. So we needed to move each individual piece so that it was acting like one big 6.5 meters wide telescope. So to do that, we pointed at one very bright star. And the first thing we saw was 18 images of that bright star. So the first thing we wanted to do is move each individual segment so that it at least moved those images of the star into the configuration of the segments. So that was our first step. But you can see that each image of the star is sort of weirdly spread out. It's not very nice and focused. So then we needed to move each segment a little bit more so that each image of the star became very crisp and sharp. And finally, we moved them one final time. So all of the images of the star were stacked as one, looked much brighter. And finally, all the different segments were working in unison at that point. So since then, we've been doing lots of work on the mirror alignment, the instruments as well. And we were actually able to take a selfie of the mirror to show the difference of how clear the image was. This is before the mirror alignment and after the mirror alignment. So everything is flat, everything is perfectly even, everything is working together here. And so we were able to release this image in March showing how each instrument could see very, very well in the infrared light. So this can be all taken in parallel because all the instruments can actually work together at once in parallel. And you can see really a giant field of stars that are very bright in the infrared. And one thing that I think is really, really wonderful is you can see in MIRI, you can actually see the gas itself in the nebula glowing because gas and dust glows itself in the mid-infrared, which has slightly longer wavelengths. And you can actually see a little bit closer here, the difference that we can have in resolution with Webb versus the Spitzer telescope, which again was 100 times smaller. So this is the best, highest resolution image in the infrared ever taken by a space telescope. And we haven't even started scientific operations. So everything has been going really wonderfully. And we recently announced that the first full color high resolution images of Webb will be released on July 12th. So we'll have a special show online from NASA, the CSA, and ESA as well on July 12th, starting at about 10:30 a.m. Eastern time. So I hope you'll join us. Obviously, we'll be like explaining all the targets that we looked at, but it'll be a very exciting time. So there are 4 instruments on the Webb telescope. 3 of them are looking at the near infrared light, so just slightly longer wavelengths than red light. So you have these 3 here, NIRCam, NIRSPEC, and FGS NIRIS. And there's the MIRI instrument that is looking at slightly longer wavelengths that needs to be cooled down further. So all 4 instruments are in this box that is located behind the mirror. And the Canadian instrument is in the very center. So we have to deliver ours before everyone else so that everyone else could sort of glom on to ours. And all of these different instruments are combinations of cameras or spectrographs or different special tools like the coronagraph, which allows you to block out a central star of a system to better directly image exoplanets, for example. So this is our Canadian instrument here. It is a double instrument. You have the guiding camera or the fine guidance sensor on top. And this isn't a scientific instrument, but it will be used for every single observation piece of data image taken by Webb. It is a mission critical component. It's essentially the eye of the telescope that allows it to point with great stability and precision on its target and lock onto its target. So it's no small responsibility for Canada to be responsible for that critical part of the mission. And we have our scientific instrument below, the near infrared imager and slitless spectrograph, which was conceived by all these different partners to look at lots of different objects, but with a specialty for exoplanets and distant galaxies. So in exchange for this contribution, Canada will get time on the telescope, which is very exciting. So at least 5% of the time on the telescope will be given to Canada. through different kinds of programs. 450 hours of what we call guaranteed time observations will actually be given to the team that helped build the Canadian instrument for Webb. And I get to work with a lot of those people, and a lot of those people work on exoplanets. That's very exciting. There'll be one large program on exoplanets, one large program on distant galaxies. But we will have lots of competitive processes. Every single year, a bunch of different telescope time proposals will be selected from the greater international community in order to do fantastic science. And many of those will be led by Canadians. So in the first year, 14 proposals for a total of 331 hours will be led by Canadians. And that starts in just a few days, essentially, where we start taking that data. Very, very exciting. We have different scientific objectives. One of the things I love about Webb is that it is a telescope for everyone, essentially. All different subfields of astronomy will be catered to. So we can look at alien worlds, looking at exoplanets, like I mentioned, and specifically the atmospheric composition of those exoplanets, galaxies through time, all the way from very early galaxies, all the way to local galaxies, how they've evolved across billions of years, the life cycle of stars from where they're born in very dense nebula type environments to their deaths when they become neutron stars or white dwarfs or black holes, and trying to look as far back as possible at the early universe to see how structure was being formed there. So I could go on about a million hours talking about all the different types of great science that Webb will do. But I am just trying to convey the great excitement that I have for the fact that Canada is part of this mission. So stay tuned. We have lots of great science. The first image is coming up July 12th. And I hope that I've convinced you that it's really wonderful that this mission exists, but Canada is at the forefront of this mission. And I hope that we'll be able to do more great space astronomy, not only as partners, but also as leaders on our own missions as well. Thank you.
Thank you very much, Dr. Ouellette. That was wonderful.
Do you want to take a break for questions at this point? I'm seeing, I think, 7 or 8 questions that I can relay from the chat and the question and answer. And I think I have them in order. So,
okay.
Okay, so the first question comes, and it relates to the images that are being released on the 12th. And I'm going to identify who asked the question, if that's okay. It's Ron McNaughton. Thank you, Ron. And Ron's asking, can you tell us what objects, what things we're going to see?
I get asked that question a lot, obviously, understandably so. But actually, I don't even know what they are. There's a very limited amount of people who are aware of what the targets are. The science teams gave recommendations, but we are not going to find out a whole lot sooner than the general public. It'll be fantastic regardless, but I can't even tell you, even if I wanted to, I couldn't tell you.
Yeah, I'm sure. I thought that would be your answer, but hey, we're going to ask the questions that pop up.
Sure.
For sure. Okay. Now the next one, this one I think is going to be relatively easy. And I know that tomorrow night we've got Dr. Sarah Sager, and this is really in her arena. But the question is, the last name is cut off. That it's Swapna. I'm sorry, I don't see all of your last name, so I'm not going to try. But the question is, how do we detect water vapor and atmosphere on exoplanets when the planet is not directly visible?
That's a great question. And I'm actually going to pop up a slide for that.
Cool.
Yeah. All right. So how do we look at exoplanet atmospheres if we can't actually see it? So we're a tricky bunch. We're a clever bunch of astronomers. So we figured out a way to do this by looking at the light of the star when the planet passes over. So we mentioned a little bit what the transit method of exoplanet detection is, and how we're really looking at the light of the star and the effect that an exoplanet has on the light of the star, the dimming of that star. But something additional can actually happen if you have a very, very sensitive tool, like the nearest instrument, for example, on Webb. So when the planet transits over the disk of the star, the rocky part of the planet is blocking out light, But if there is a thin atmosphere around the planet, starlight can actually stream through that atmosphere, and some of the colors of the starlight, or the wavelength of the starlight, will be absorbed by specific molecules or atoms in the atmosphere of the exoplanet. And we know what signatures or what lines will be absorbed if water vapor is there, or if oxygen is there, or carbon dioxide. And so when this happens, we can then use a spectrograph, an instrument, to sort of spread that light, turn it into what we call a spectrum, and then we can see these different signatures of the star. And some of these signatures are what we call biosignatures. So different of the types of these molecules and different combinations could potentially mean that there is biological life producing those signatures on that planet. Probably very simple life, not very complex life, but we can do this without being able to see the planet directly using this method called transit spectroscopy.
Thank you. Thank you very much. Okay. Next question comes from Randy Atwood. And Randy Atwood's been a long time society member and journalist bringing space exploration news to Canadians for years. And Randy's question was, he thought that the James Webb Space Telescope was going to first spend time looking at TRAPPIST-1. So this really is around what's the schedule of events? What are the priorities for Hubble, JWST?
Yeah, so there is actually a schedule that's out for the first few weeks and months. Basically, we've scheduled out most of the first year, and even though TRAPPIST-1 will be observed very early on, we do have constraints. Observing constraints for certain instruments, because you want to observe TRAPPIST-1 at the right moment when, well, number one, it's visible in the field of view of Webb, and when something interesting is happening. So TRAPPIST-1 has its transits going on fairly frequently, so that helps. But we need to optimize the scheduling of the observations on Webb to make sure that we fit in all these different constraints, because some targets are only visible some part of the year. Some people only want the observation done when a transit is happening at a specific time. But we are lucky. TRAPPIST-1 with the Canadian program will be observed very early on in July. So one of our PhD students at IREX, Olivia Lim, will actually be getting some extremely early data, and she's very excited, and also is feeling the pressure to reduce that data as fast as possible.
Awesome. Thank you. Now, this one comes from close to home, Maury Portnoff from Montreal Center. And this should make you smile. Who was your inspiration for the Halloween costume?
So actually, it's an interesting thing, because my partner has been building big cardboard box Halloween costumes for the last like 15 years. Every year, he chooses a weird household object, like a box of Pop-Tarts or like a Duracell battery or something like that, and he builds a perfectly to scale Halloween costume of them using cardboard boxes. So I thought, okay, I can make something out of cardboard that's perfectly to scale, but I don't want to be like a cereal box. I'm going to be James Webb. So he was actually a big inspiration in me making my Halloween costume last year.
Nice. Well, speaking of JWST merchandise, and notice your necklace is a replica of the mirror. That's an interesting piece of merch that the Royal Astronomical Society of Canada might want to offer through our website.
Yeah, definitely. So if you go on a website called SciChic, so SCICHIC, it's actually oh no, they're out of business, unfortunately. But Startorialist is a website and a company that is headed by two astronomers who also like fashion a lot. So they have put together a bunch of astronomy themed clothing and jewelry and everything.
Nice. Thank you. Thanks for sharing that. So this is another one from Randy Atwood. And Randy says, the unfolding and setup of JWST after the Christmas launch was promoted as many hundreds of things that had to happen, or the mission would be a failure. Was this to prepare us for the worst, or did mission management feel there was a good chance that all would go well, but just in case, we should be cautious?
It was a little bit of both, really.
Mhm.
So one of the key things for us in the mission, and was especially pushed by people like me who work a lot on the communication side, is almost complete transparency during this whole entire mission. So that's why we didn't go radio silent during the 6 months of commissioning. We had people, we had media inside the operations center at the Space Telescope Science Institute. We gave and continue to give very, very frequent updates on what is going on. And so we wanted to be transparent about how complex this deployment was going to be. We were confident that we had done our homework and we had tested everything that could go wrong. We were fairly confident things were going to go right, but we wanted to be transparent that something might go wrong, because this is something we've never done before. So it was an exercise in really letting the public know exactly what was at stake.
Thank you. Thank you. Tom Sobakan from the Windsor Center asks, will JWST be a useful tool to study the black hole at the center of the Milky Way?
Yeah, absolutely. So a lot of people love black holes, obviously, and James Webb will not necessarily be the best tool to study stellar mass black holes, smaller ones. They tend to be very well observed in X-rays, but supermassive black holes at the center of galaxies, James Webb will be a fantastic tool for that, because it will have very high resolution, and it will actually be able to track the movement of stars that are spinning around the centers, the centers of galaxies where those supermassive black holes are located. So we'll be able to do things like pin down the mass of these supermassive black holes with much more precision. And not only our own supermassive black hole, but those of neighboring galaxies as well. So Andromeda or M87, which we got a nice picture of in 2019. So supermassive black holes is a very important study field for Webb.
Nice. I'm going to combine three questions on this one. They come from Laurie Roche and Max Alpazar and Christopher Bolte. So the questions aren't necessarily the same, but I think the answer is related. So one of the questions was, what would have happened if only 16 or 17 segments worked and not all 18? Another one was, is it true that there was a micrometeor impact, and what's the effect of that? And I think those are all related.
Yeah, and I just saw another question pop up about the micrometeorite. So obviously, this is something that we wanted to consider when we built the telescope. There were actually tests that were done to make sure that the materials selected for the mirror were fairly resilient if they were impacted by a micrometeorite, because we know that that can and will happen in all likelihood during the lifetime of the mission. So to give you a little bit of insight, I can tell you, when we really celebrated the fact that we had a functional telescope was when the secondary mirror was deployed. Because really what you need a primary mirror to reflect part of the light, and then a secondary mirror to feed the light back into the instruments. Even if the wings didn't go out, we would still have a functional mirror and functional telescope. It would be a smaller telescope, so it would be disappointing in that sense, but the light could at least be redirected towards the instruments. So if some of the segments were to not work, we would have to move the other segments around to compensate. We would have a slightly less powerful, slightly less effective telescope, but as long as the light is redirected towards the instrument, it would still work. We would still make it work. So that is sort of the important thing to remember. We were not one segment away from having a total failure. It's not mission critical. In terms of the micrometeorite, it is true. At the end of May, we were impacted by a micrometeorite that was slightly larger than what we had been able to test here on Earth. Because the telescope has been doing so well, the telescope is continuing to perform above and beyond our expectations, even with that small dent in the mirror, essentially. And we had to move that segment in order to compensate for the slight deformation in the mirror. But we knew stuff like that was going to happen. And one of the nice kind of offshoots of that is Webb is sort of becoming, as a guinea pig, an instrument that helps us better understand the density of that environment in terms of micrometeorites as well, for future missions as well. So that is like a good thing, but I'm still hoping for not too many micrometeorite hits, because I want the mirror to be as good as possible.
There's actually a question about predictions on might it be hit again by a micrometeorite, but we won't test you on that one. But it's interesting that the segmented mirror design adds a degree of resiliency that we wouldn't see if it was a single mirror, of course, like Hubble. Yeah.
Absolutely. So yeah, we learned our lesson with Hubble.
Yeah. So Alan Dyer, great talk this afternoon, Alan. Thank you for that. Is there a type of observation that the Canadian instruments will be primarily used for, or will be best used for? And he says, thank you too.
Yeah, of course. So yeah, the nearest instrument, the two really, there's three modes that are really key to the instrument. One is called SOST, or single object slitless spectroscopy, and that's to really do those atmospheric studies of exoplanets. It's a tool that was specifically developed to do that kind of study, and it's no small coincidence that the principal investigator of the instrument is also the director of an exoplanet institute. He was sort of serving his own interests when he was building the telescope. So it'll be able to do certain types of study for atmospheric composition of exoplanets better than other instruments on Webb. The other one is called WFIS, WFSS, or wide field slitless spectroscopy, and that will allow us to simultaneously take the spectrum of thousands of galaxies, which is really useful in clusters of galaxies, which can have lots and lots of members. And that is an order of magnitude larger than what the NIRSPEC instrument can do, which can only look at only hundreds of spectra. And the third mode is called AMI, or aperture masking interferometry. And that is sort of a similar technique that was used to take a real picture of a black hole, but it's sort of condensed inside the instrument itself. And it'll be able to take real images of exoplanets, protoplanetary disks of solar systems being formed. So yeah, solar systems being formed, exoplanet atmospheres, and clusters of galaxies. The Canadian tool is very, very good for it.
Nice. I'm going to jump out of the sequence because there was a question too about, can we use the JWST for work within the solar system? As you mentioned solar systems there, I thought it might be, and I'm starting to get the name on who posted that one. But at any rate, yeah, can we use it intra-solar system?
Yeah, absolutely. So actually, because of the fact that it's an infrared telescope, and if you turned it towards the sun, it would completely fry the optics and everything and destroy the telescope, we can't look towards the sun. So everything inside of the orbit of Webb is off limits. So we can't look at the sun, can't look at Mercury, Venus, the Earth, the moon, but everything outwards is fair game. So basically from Mars onwards is something that we can look at. Are we going to use time on Webb to look at Mars? Not necessarily, because we have boots on the ground to do better observations. But there are certain things like the ice moons that are around certain planets like Jupiter and Saturn, which will be great targets for Webb, because sort of in a similar way to transit spectroscopy, Webb will be able to look at sort of the water being gushing out of the cryovolcanoes or the ice volcanoes on their surface, like on Enceladus here, and try to figure out what kind of molecules and atoms are in the liquid oceans below. And there are also some great observing programs for Neptune and Uranus, which have been very neglected by probe exploration in our solar system. So yeah, lots of really fantastic solar system observations too.
Excellent. That was a great question. That was from Max Alpizar. John Marchese asks, how do we watch with you on July 12th?
So there will be a link that's going to go up on the NASA Live website. So on YouTube or on their website directly. And so I will be at the Canadian Space Agency while this is going on. And all the different partners will be calling in and presenting their instruments first image. So that'll be really exciting. So it'll be online on NASA.
Nice. Dr. Nicholas David from the Calgary Center. I just want to do a shout out to Nick. He's been a prolific speaker for our center. He asked a question around, will it be hit by a meteorite and what could happen? What would the team do if it happens? You've answered that question, but I didn't want to skip Nick's question. Sure. Emily LaFleche. Emily is a PhD student at Purdue. She was a founding chair of our Next Generation Committee and her
I know
work
Emily.
towards,
She was
you know,
one of
Emily.
our interns at
Yeah.
IREX.
And Emily, I know we'll be announcing it officially tomorrow, and everybody kind of knows it already. But Emily is the recipient of the President's Award. I get to pick the recipient of that. So for her good work in starting up that group and giving us that kind of focus as an organization. Emily asks, how will JWST and LUVEX, the eventual LUVOIR-HABEX combo, be able to work together to inform future studies on exoplanet science? And she says, thanks so much, Nathalie.
Yeah, so I have a little bit of a slide here as well. So for those of you who don't know, like I mentioned, these telescopes are built decades in advance. It takes a long time to do them. So we've been trying to figure out what comes after Webb, and we've thought of what we used to call LUVOIR, we now call it LUVEX. It's essentially maybe we're hoping bigger version of Webb. You can see how it's dwarfing Hubble here with a very similar concept. So this was like an idealized version. We might have to downgrade our ambitions a little bit. But one of the great things about LUVOIR or LUVEX is that it would look at both at simultaneously ultraviolet, visible, and infrared light. So all different kinds of windows. So one of the ways that the two missions would work together is that Webb is basically doing a lot of pathfinding for LUVOIR. It's the first big deployable mission. It's the first mission that has the exposed mirror like that. So where we're more vulnerable to micrometeorites. So Webb is really going to be a pioneer to figure out how we can do LUVEX. Even with the very optimistic estimates for the mission lifetime for Webb, the instruments might start failing even though we have fuel for about 20 years. And LUVOIR probably won't come to be until the 2040s. So who knows what can happen? Maybe there will be an overlap in the mission, but it's not super, super likely. So the way that they're sort of working together is that Webb is trying to figure out the best way for LUVOIR or LUVEX to be in the future. So LUVEX will get to benefit from all the lessons we learned with the Webb telescope mission.
Excellent, excellent question. Thanks, Emily. And thank you, Nathalie. John Nagel asked, will the JWST be used for follow-up on gravity wave observations by LIGO?
So that's a very interesting question as well. And for follow-up observations, typically, we like to do the multi-messenger astronomy where we're looking at the progenitor of these gravitational waves at all different kinds of wavelengths. So we saw that with some of the gravitational wave detections where all these telescopes all over the world basically turned around and looked at where we thought the gravitational waves were coming from. So Webb can certainly be an interesting tool to look at in the infrared, but typically, because these are such violent events, we are often looking for neutrino signatures, X-ray signatures as well, sometimes in the visible light as well. Infrared can be interesting, but it's not typically the first thing that you expect when you're looking at a progenitor of a gravitational wave, but certainly it can partake in those multi-messenger astronomy missions.
Thank you. Brian and Marlene McCracken ask, the Canadian contribution seems to be a crucial component to the entire operation of JWST. Did the Canadian design engineers build in redundancy in the event of a failure of a subcomponent?
So we don't like talking about failure, but we like to plan for failure, certainly. So there are redundant systems within each instrument, but I'd say the most important thing in terms of redundancy is that there is redundancy between the different instruments and different modes on the instrument. So even though there are certain aspects of different modes on each instrument that differentiate the instruments from one another, for example, if the near-spec instrument were to fail and not be able to be used as a spectrograph, NIRISS can sort of pick up the slack because it has a spectrographic component to it. NIRCam has a coronagraph, but so does NIRI as well. So if a component fails on one of the instruments, other components of other instruments can help do a similar kind of observation. It won't be exactly the same because they weren't built exactly the same, but there's a lot of redundancy within the instruments, but also among the instruments.
Nice, nice. Well done. Samantha, why don't you come back, turn your camera back on? And I think Samantha she posted a question, but she couldn't post a question in the Q&A, but I think you answered it. But Samantha, did you take note of where that necklace came from?
I was trying to take note. Which one is I will say, even I've had like hexagon earrings that look like they're supposed to be bee honeycombs, and people every single time say, "Where'd you get your James Webb Space Telescope here?"
That makes me so happy, because sometimes I'm like, where did you get your honeycomb necklace? So sometimes people think I really like bees rather than astronomy.
Can you repeat was that student or the science people who work on it again?
Sorry, say that again.
Can you repeat where you said that you noted a shop that was open?
Oh yeah, it was just posted again.
Yep.
Phil posted the link in the chat. Yeah.
And Jim Small commented that it's sold out.
It is a very popular mission at this moment.
Hey, but if there's any makers out there and you've got your, if your 3D printer is not doing something right now, Phil, go ahead. You got a comment.
I was just going to say there are a number of 3D models of James Webb available for 3D printing out there. Eric Briggs, our national secretary, produced one of them, and it's in our office right now. It's lovely. Mm-hmm. He's apparently working on a more detailed 3D print model from a different source, but go to places like Thingiverse and such, and you can find various printable versions of JWST.
Excellent.
We do have a question from our YouTube friends. Mr. Dillon says, will you be able to make another telescope like James Webb much faster and more efficiently, since we have JWST perfectly how we wanted it? Or is the hard part is testing rather than the engineering of the telescope?
So here's the thing. We can learn lessons from a telescope, but typically astronomers are not satisfied with replicating something. They want to be like, all right, let's make it even better, more efficient, or use better, bigger, newer technology. So we'll definitely be able to learn lots of things through the deployment and how it acted with the shape of the mirror, the configuration, all those different things. But for what's coming up afterwards, we're going to want to make the instruments better, different, using new technology that we've been able to create. So astronomers like being the first to do something. And when you're the first to do something, it's never easy. So we can learn from what we've done before, but we will continue trying to be innovators. And that's the part that takes a lot of time.
So what do you think is going to be the next big telescope in the wavelength that we don't have an idea for now, but what wavelength do you think we would want to focus on next?
So one thing that I can mention, and again, I'm so prepared, right? I have little slides for everything. And I'm really happy that I get to mention this. I wanted to mention it in the main talk, but I ran out of time. So we know that Hubble is functioning now, but it's getting older, and sometimes it goes into safe mode and everyone gets very, very nervous. And once Hubble goes offline, Webb will be up there doing great work in infrared, but we're going to have this big gap in the visible side of things in space astronomy. So in Canada, we're hoping to send our own version of Hubble called Castor, which, as you might know, is French for beaver. So a really, really Canadian, Canada-led mission. So Castor stands for Cosmological Advanced Survey Telescope for Optical and Ultraviolet Research. So it's going to look at blue light, ultraviolet light, and it's going to be our very own little Hubble, looking at very similar wavelengths to Hubble and also Galaxy, which was an ultraviolet telescope, but it has a field of view 100 times that of Hubble. So in this picture here, you can see the field of view of Castor in the white and in the red. That is what Hubble can see in one snapshot. So in terms of taking images of lots and lots of the sky, it's going to be a great tool. And I'm using it's going to be, but it's not funded yet. We are still trying to convince Canada and other international partners in the UK and India and the US to participate. But this would be such a fantastic thing for Canada to have a mission that we are leading. We're not just a partner in the mission. We are leading this mission with partners, of course. And this would sort of fill in that gap if Hubble were ever to stop functioning. So I'm very optimistic we'll be able to get this funded. It would be set for launch in 2026, 2027. And it would have so many benefits for science and astronomy and STEM in Canada. So I'm really hoping that this mission will be the next great mission Canada partakes in.
Wonderful, wonderful. I think we're running out of questions. Nathalie,
one more.
One more?
But
Okay.
I think that kind of answers. Are they already planning the predecessor of the James Webb? Or are they just going to be happy with the James Webb for a little bit, considering the time frame it takes?
So yeah, we were planning for different options of the successor of James Webb, and LUVEX is sort of the front runner for that. So right now we have a few different telescopes that the community is considering as the next flagship mission for NASA. LUVOIR/LUVEX is sort of like in the optical area. LYNX is another mission that's being considered in the X-ray. Nothing is funded yet, but these are the missions that are being studied essentially. But we won't see them for a few more decades. So Webb is going to be the big fish in the sea for at least a few decades.
Thank you.
Excellent. Thank you so much. Nathalie, it was a pleasure to virtually meet you. And I love how you were so easily answered absolutely every question and actually had backup slides for it.
I come prepared.
Like
Thank you so much for having me. Yeah.
Oh,
yeah.
It was a
Almost like
pleasure.
she's in science communication.
So on behalf of the entire society, truly, thank you so much.
Thank
Wonderful,
you.
wonderfully done.
Thank you. Thank you again.
I'm going to share screen just for a moment, just a logistics thing. So for the folks that are registered, we've got two things coming up. Observing Across Canada, where we have virtual solar viewing from the West Coast and nighttime viewing further east. So we're chasing the sunset and following the sunset, depending on what part of the country you're in. And of course, we've got social time in Gathertown, where Dr. Philip Groff, who you can see on screen, will be our bartender it's now the 80s. What is it?
The 80s bar now.
It's
we
an
took
80s
down the
bar.
tiki bar. It didn't match with the theme of the GA.
Yeah. And Nathalie, if you'd like to join us, this ragtag group for a social activity, we're going to be in Gathertown. All of this commences at 9 p.m. Eastern, 6 p.m. Pacific. And of course, from your from the attendee hub that everyone knows how to get to, because you use it to get here, click on the links or the schedule and you'll see these two events, and join in at 9 p.m.
Gathertown's always open too, so you can use it throughout the weekend. If you have a session you're really interested in, you want to chat with someone afterwards, that virtual space is open as well.
Cool.
So
thanks everyone, and to all of the attendees, thank you for joining us this evening. I hope you enjoyed. I know you enjoyed it. I know we know this group. All right, so we'll see you all in about a half an hour.